As I said, I don't propose to lead the entire discussion. I just want to kick things off early in the morning when I'm awake. I seem to become non-functional, dysfunctional from lunch on. I came here, I should say I'm very grateful to the organizers for supporting, not only for allowing me to speak right now, but for supporting the entire visit. And I come as a information paradox skeptic. That is, I've never been convinced that there's really a problem. But I've also been acutely aware that that may be due to my ignorance, because I have no strong opinions about quantum gravity at all. My own contributions to this field have been concentrated at this level, and even that, in as far as any relevance to the subject matter of this conference, stopped about 20 years ago. It was there. What happened to it?
Can we project on the screen? Yeah.
So I would like to review a little bit of history, which is largely the history of my own understanding of the subject, but I think it's chronologically accurate, and of course I will welcome anyone else who wants to interrupt at some point. But to start with, in the 1950s and early 1960s, there was quite a lot of talk about the existence of black hole singularities being inconsistent with the conservation of baryon number. And I never really understood what that was all about. It seemed quite clear to me that if you had a singularity, a particle could reach the singularity in a finite proper time and disappear, and who cared? That just meant that the topology of the space was such that the particle disappeared. That's not inconsistent with conservation of charge or baryon number or anything else. In our theories, conservation laws basically come from, let's write it here, local conserved currents, which under certain conditions can be integrated to give global conservation laws, but there's no reason why in a complicated geometry and topology of space that this should give some quantity that is absolutely conserved if the structure of the space says otherwise. So I never understood why there was a problem. Then we began doing quantum field theory on a curved background without considering back reaction. And we get similar situations where, to draw the famous diagram, we have some kind of flux being created that goes out here, some kind of negative flux being created that goes in here. And if you want to consider a Cauchy surface for this space-time, when you push it into the infinite as far to the future as you can, it's going to be like that if you are going to stay outside the horizon. Everything is perfectly unitary, as people say there. Or if you're going to allow observations inside the black hole, you can go in there and get something that's perfectly unitary. No problem. You get to here in a finite time. But again, who cares? Nothing is, as far as I can see, is wrong or strange there. But then, see, I never really thought very much about this problem until recently, when I suddenly began to realize why people were concerned. That if you assume that by energy conservation, the horizon must actually be shrinking and eventually gets to zero size so that the singularity in some sense disappears, carrying lots of the incoming stuff with it, then that does seem a bit strange. So let me tentatively draw a line across here and take a poll. Is there consensus that there is no paradox above this line?
Up, down to that line.
Yeah, there's no paradox down to here. If so, we have at least one consensus.
We can't measure it. Can we project that screen again, George, please? So you want us to think about if there is an information paradox or not?
Is there an information paradox within the theory at this level or this level?
Okay, let's take it forward.
Can I rephrase the question?
Yes.
Is there a way to get the Hawking-Bekenstein entropy with those only above that line in a way that makes sense and is completely consistent with statistical mechanics as we know it?
Again, I plead ignorance. I'm not a statistical mechanician.
But
So,
that's a different question, but it's part of what the information paradox contains. Where is the number of states that go into the entropy formula? So you want to separate
Let's
that
take
as a
two
question?
votes then.
Then-
Let's
But
first
if-
go through the
Okay.
more general question of information loss and then go through the
could
details.
I just respond to Emil's point? So this, which I drew here, refers to this, right? So I should have drawn the line down like that. Now,
So
in
let's
this picture, nothing has shrunk. So is there any problem with having lots of entropy there?
I still don't know how to calculate it.
Well, maybe there is no paradox, but at least there is a difficulties.
Yeah.
Because the point is, how shall you define the Riemann function? Or in other words, how will you define the vacuum state on a curved background? And we know that,
Okay.
for instance, we use the Bouloir state. It's perfectly defined outside a star, but if the star collapses, we have to use the Unruh vacuum and all that. So in general, I think we didn't know the precise answer on how to do precisely quantum field theory on the general background.
Okay, there are two questions there. One is the question of what the quantum state is, what initial conditions to choose. And I think that if you start with a stable star back here and then it collapses, a strong argument can be made that the exact state is well approximated in this region of space-time by the Unruh state. The second question is what to do with it when you have it. Can you actually do any calculations? And that's a technical question. As long as we're simply not discussing back reaction, but simply taking quantum field theory on a fixed background, I think there is the conceptual problems were settled in the 1970s. The technical problems remain because these calculations are hard.
So then I gather what you're saying is that if you don't worry about the evaporation of the black hole, the formalism is fine. Yeah,
Expectation values of stress tensors.
right. But now we do have, and once we get to the second half of your blackboard, then we do face the question of what happens when the black hole, as the black hole evaporates, and what's left, and do you get
Right.
back all the information and so on, things like that.
Okay, so as I see it, the big controversy is what surrounds level number 3 and the issue of whether passing to level number 4 will or will not resolve it. So, do we agree with that? So, Bernard?
So I don't think I quite understand your position even on one. It may not be that it's controversial, but I'd like some clarification. So Just purely classically, forgetting all quantum physics, we can make black holes, classical black holes, different ways. And we can't, and once we have a black hole, we can't tell how it's made.
Okay.
So at a classical level, I would suggest that in some sense that implies there is a loss of information in having a black hole. Because knowledge about how the black hole formed is not determined or determinable from the classical matter outside it. So I wouldn't say it's controversial, but I find it difficult to vote in support of saying there's no information loss at level 1 in this sense.
Certainly, if we're going to time reverse the evolution, we have to give some initial data to tell what's come. You turn the picture upside down, stuff is coming out of the black hole, right? And you have to say what it is.
If you're asking, is it
And
deterministic?
it's not determined by the black hole.
So if you're asking, is it deterministic, then I would say yes.
If I understand Steve, if you include quantum field on curved space-time, you will end up with Hawking radiation, and that produces a time asymmetry into the setup of the problem. So you cannot reverse the situation. If you have classical physics only, then you can always reverse.
Right, but above level 3, he's not allowing evaporation, so
He's allowing quantum field on curved space-time produces.
No, level 1 and 2 have no back reaction.
Yeah, back reaction is a different story, but quantum field on curved space would give you.
You're arguing about the definition of evaporation.
Okay.
Right. I have Hawking radiation.
Yes.
But I'm not allowing it to change the background space-time and make it go away.
Even for level 1, I think you need to be a little clear about what we're just talking about. Because if you have a classical black hole, then in a sense you do have the paradox that Jacob Bekenstein identified. Namely, before there was any notion that the black hole had any entropy, you could throw hot objects into the black hole and decrease the entropy of the universe. Now, of course, Jacob saw a way to correct that by assigning an entropy to the black hole. So I think even at level 1, there's a potential paradox if you don't include Jacob's idea of black hole entropy.
I mean, to follow up on that, seems to me the logic of your position is, who cares? Entropy decreases because it goes through the singularity, and I don't care about the second law at all. It goes into some other space or God knows where, and that doesn't matter to me on the outside. So.
Yeah, I could shoot hot matter off to infinity too, right? And say that it's no longer relevant.
So on point 2, you would argue that you have outgoing radiation, but you have something totally unphysical. The total energy in that outgoing radiation is infinite. So this state that you put on this space-time is nothing that we'd ever want to, we could build physically or would be interested in physically. You may be able to say, define it, but it's not, its relationship to physics is thin. And to say that it implies you have outgoing radiation in a space-time is, I think, not possible. In a physical space-time.
You're saying the Unruh state evolves into something that is singular on the horizon.
No, I'm worried it's scry. You say you have scry plus. You say you have outgoing radiation there, and the total energy.
It's not infinite density. It goes on forever, eternally, but
the total
energy
amount going to infinity is infinite.
Right.
And we can't create states like that.
Yeah. So if you don't have back reaction, then you're not going to have energy conservation in that sense. You still have energy conservation for the scalar field because of negative flux over here, but you're right. There's a total infinite amount going out.
Can I make a suggestion? The big question, of course, is what happens after the black hole starts evaporating and so forth. And you might say that the no-hair theorem is false because, at least in the way that Stephen Hawking is looking at things now, you're actually saying there is some kind of here on the horizon, event horizon of the black hole, these sort of holographic remnants, you might say, of what went in. Well, that's a violation, in a way, of the no-here theorem. But the no-here theorem doesn't work in that case. You can't prove it. So I think this is one way of getting a solution to the problem, and it would be very interesting to see what if it works. It's a very natural kind of solution. There are other possible solutions as well. But
Well, I'm about to turn matters over to other people because, as I say, I don't know much, really know much below here. But I see Paul has something to say.
I wanted to hear what you had to say about 3 and 4.
Oh, well, what I have to say about 3 and 4 will not be at all conclusive, but I come as an emissary from another conference. There were 2 conferences on this same topic this month, and I believe I'm the only person who attended both. So you may think of me as the last photon that arrived before these 2 groups went over each other's respective horizons. Okay, this conference was 2 weeks ago at the Perimeter Institute, and it was in honor of the 70th anniversary of Bill Unruh. And it was represented, heavily represented. There were people like Bill Unruh and Bob Wald, who believe that information is lost in singularities, even in quantum gravity, and it's not a problem. And they were so strongly, feeling so strongly on this, that I had the impression that when I got here, I would face the opposite party, and the room would be full of people who are violent proponents of firewalls and fuzzballs. But that is not what happened. There have been people talking about firewalls, but I get the impression mostly grudgingly, trying to defend the more traditional general relativity and quantum field theory from the more modern speculative ideas.
Yeah.
So what I want to do is just briefly report my understanding of the other position as represented extremely well by Bob Wald in his talk there and his previous talk at the Santa Barbara workshop, and list the alternatives for dealing with steps 3 and 4.
so are you saying they argued that there is no information paradox?
That there is information lost, and you shouldn't be upset by that.
Well, Steve, before we move to 3 and 4, can we take a vote on, is there an information loss paradox with this open-minded crowd here?
Still up here?
Yeah.
Okay.
Let's take a vote.
Okay. Is there an information loss paradox at level number 1?
So I,
Shall I rephrase the question?
there's information lost, but it's not paradoxical.
Okay. So is there? Yeah. That I tried to place the emphasis on the paradox rather than on the loss.
Well, it's certainly a paradox if you have Hawking radiation going out to infinity and you're not changing, you're not having back reaction. I mean, that's a paradox.
Well, it means that's a breakdown of the model, surely, but whether it's actually a paradox. Okay, so.
Let's take a vote.
Okay, vote on number 1. Yes?
Yes, what?
Yes, yes, there is a paradox. No? Number 2. Yes, there is a paradox. Okay. No.
Repeat the statement, please. I don't know what I'm voting on.
Okay.
I want to hear about 3.
Is there a paradox at this level? How would I describe what? Stephen meaning Stephen Hawking.
Use the microphone, please.
His first, I don't remember everything that was in that paper, but I think the original paper was at this level. And then there was a later level paper at this level, which is the one about breakdown of predictability. Right?
Can we hear about what Bob Wald says?
Yeah, so let me, this is Wald's hierarchy, for lack of a better word, slightly edited by me. I will write the things in the opposite order from the order he gives them. Starting with 0, which is his own position that information is lost in singularities even at level 4. And his mantra is the creation of mixed states from pure states by tracing out certain degrees of freedom is not a breakdown of quantum physics. It is a prediction of quantum physics. And there's no reason why one should start modifying agreed upon quantum physics and agreed upon general relativity at the level of a macroscopic black hole where we think we understand things in order to try to avoid that.
Can I ask a question there?
Mm-hmm.
Unitarity is also a prediction of quantum physics, and that's violated.
What?
If we have any unitarity is also a prediction of quantum physics, and that's violated by singularities.
No. When you go from a Cauchy surface to something smaller, you should go from a pure state to a mixed state. That's what quantum physics says. It's not a violation. It just means you're looking at a subsystem. Okay, so let me go on to complete this list. Let's see, the next one I think is remnants, where the idea is that quantum theory modifies the collapse to such a extent that the singularity is averted and you have something left over, Planck size, something or other left over. And I would put up here something he didn't mention, but that Paul has mentioned, which is baby universes, where the missing degrees of freedom are still somewhere, they're just not connected to our universe. Then there is what we can call final bursts. Which says that something happens in the very late stages at Planck scale or somewhere getting down toward Planck scale that causes the black hole to explode, dissipate, or whatever. And the partisans of this are, of course, Hawking since 2005, Bardeen, Hayward, Frolov, and others. Now I'm going to put another line. And then the remaining things are those that propose drastic modifications of physics at fairly early times, when we are looking just at a traditional macroscopic black hole, and those would we're going backwards in time here. The farther you are on the list, the earlier and more drastic the modification is. So the firewalls go here. The fuzz balls and EPR equals ER wormholes go there. And I think we should insert here Laura's fireworks. So as I understand it, this is a kind of burst, but it occurs much earlier than this. So here is where the controversial line is. The position of Wald and Unruh, with which I'm sympathetic, although I don't know enough to make a strong statement in that direction, is that all these things are rather drastic modifications of physics that we think we know. These are all, for some reason, regarded as physically unsatisfactory by the proponents of these. And I think at that point I should surrender the floor to other people who have more to say. My personal position is, Wald's position is this, but he also will allow one of these, but say, I don't see that it solves any interesting problems. He doesn't really say that these are impossible. My personal position is that it might well happen, for all I know, that when the full problem is solved quantum theoretically, that the outcome might depend on the initial conditions, or say the size, the mass of the system, just as far as supernovae. If you have a fairly small star, you have a nova and it collapses to a white dwarf, if I remember correctly. If it's bigger, it collapses, you have a supernova and it goes to a neutron star. I don't see why you can't also have some systems that go to true singularities and some that go to remnants and bursts. But now I'm just speculating completely beyond my expertise, and so I will sit down and shut up.
Would you like to? On the origin? What? Would you like to take the podium?
I don't think I have any great pronouncements to make. I mean, I can spell out very quickly my position on many of these questions, which the bottom line is I don't know. But I think early on, if you ask, are there paradoxes at the classical level or at the level of quantum field theory and curved space-time, I think not if you have defined things carefully. At the classical level, as long as you understand there must be a resolution to the Bekenstein paradox, then black holes must have some kind of entropy, then there isn't a classical paradox. At the level of quantum field theory and curved space-time without back reaction, as long as you say there must be some back reaction someplace, but we're not yet taking it into account, then there's no paradox. Where things get tricky is then when you include back reaction, you ask what's going to happen to the black hole, and then things are a lot less clear. I think I would add one thing, though, to the list there, and that is the issue, can there be correlations in the outgoing Hawking radiation? Mm-hmm. Certainly the typical thing that we might think of is that we take a piece of paper and write a message on it, and then burn the paper and atomize the ashes. Then nobody feels that that's paradoxical. But where the information go, it went off in phase relations between the various photons, which we have no hope of catching them, but they're there. And that could well happen with the Hawking radiation for some reason. And if I understand things like Gerhard and Twift's resolution, and presumably the only way to use Malcolm and Stephen Hawking's ideas on super translations is that these have to leave an imprint on the outgoing Hawking radiation. how that happens and whether there's a plausible mechanism is not clear. And that's just, I think that's kind of the level of, and of course for full quantum gravity, I think it's too early to speculate. So I think that's about all I can say.
Well, I can ask a very simple question. Back in the 70s, when you were all working on deriving black hole radiation from quantum field in curved space-time, what is the origin of Hawking radiation? Is it produced during the collapse of the star? Is it produced long after the black hole has formed and the horizon and singularities are there? Is the collapse crucial? Do you need that in order to produce particles?
So I think we tried to answer that in this very simplified model we did with Chris Stevens and at Tufte, where we collapsed the shell to some point, and then by an act of acting as supreme beings, we reversed the shell and made it go out. So it's not almost everywhere this space-time obeys Einstein's equations, except at the bounce. And what we found as we allowed the bounce to go closer and closer to the horizon, that the outgoing quantum state became more and more like a thermal state. So in this geometry, there was no horizon anywhere, there was no singularity. Well, there was a singularity at the point of the bounce, but there was no horizon. Even though the outgoing state became more and more thermal distribution, globally, we had a unitary evolution. So there had to be correlations that we couldn't find, spread all over Scry Plus, that preserved the pure state, even though locally, next to the bounce, the radiation going out became more and more thermal-like. So I think we know the answer to that.
Thank you. So the collapse of the shell was important, and I know Philip has a beautiful review of the subject. I think you calculated the Hawking radiation in your review paper.
Well, I think it's a kind of reorganization of the definition of vacuum according to the Cauchy surface you consider. And if you remain outside and make only measurement outside the horizon, obviously you have to trace on the inside Hilbert space, and this produces an effect of the thermal distribution. But it's mainly a redefinition that was linked to my first remark, a redefinition of the vacuum that you need when you evolve in a collapse framework.
Yeah.
You can, what Bernard was saying, you can do the same thing with an accelerating mirror. So you can pick one that gives you something going very close to thermal output, and then just smoothly join it to a uniform velocity at the end. And so all is good up to that point. So it doesn't seem to be connected with the horizon. Another telling case, I had a student many years ago look at uniform acceleration in a compact space. So there is no horizon because you go round and around and the light cones go round and around. So, and again, you get the thermal result. In that case, you accelerate forever. You get the thermal result, but it's thermal radiation appropriate to a compact space. So you have discretized modes. So I think that...
But the acceleration is crucial. So one could not, obviously could not get particle creation if the mirror was not in uniform acceleration, or if the star was not collapsing.
But I must take you to task about your terminology, which is a lot of people conflate that when they say the origin of the Hawking radiation. What do you mean by radiation? Are you talking about particles, or are you talking about energy fluxes?
Well, the stress energy tensor is the only thing that makes sense in this case, because particles don't have a meaning.
A lot of people just flip from one language to the other, which confuses lots of people. And if we're just clear about there is a T menu in 2 dimensions, we can write it down. Now, you can argue, and Stephen Fulling was taking me to task about how to represent the terms in that, you know, where they most appropriately belong and so forth, and that's possibly an issue. But it's only an issue of semantics, really, because it's there for all to see. And we can predict from those calculations exactly what any given observer moving on any trajectory is going to see, and everything's got to be self-consistent because it's a covariant object.
Yeah, if I could just comment on those models, though. Of course, the important part of that is that what you've discussed is only one side of the mirror.
Yes,
Those
yes,
particular trajectories are ones that accelerate away from an observer and emit a thermal spectrum of particles, let's say, to the right.
Yes.
But of course, there's also correlated radiation going off to the other side of the mirror.
So it's
and
taking
as
the
long
information
as you take
away
those
to the
into
left.
account, of course, there is always a pure state.
Right.
And including if you wrap around the universe, if you include what goes off on both sides of the mirror, then definitely everything stays in a pure state.
Right.
It's just that in this model, the thing that goes off to, let's say, the left side of the mirror away from the observer is analogous to what goes down the horizon.
Right.
Except here it's not lost.
Yeah.
It's available to be caught later.
Can I just make a comment? When I was working on my PhD thesis in the 1960s, I worried about something like an information loss, namely pairs of particles are created by the expanding universe, and one pair goes off into a distance and the other one is near us, say, and so we can't really observe the other member of the pair, but it's correlated. And it's something like if you look at the Einstein-Rosen-Podolsky paradox, then we should still be able to find, I was wondering, is there any kind of correlation that, you know, if we make a measurement or somebody in this galaxy far away that we don't see makes a measurement of one of those photons of that pair, it's correlated with the photons sitting here in our galaxy or coming toward us, and we should then have our photon somehow correlated. There's no obvious way to get the correlation between the two because of relativity, and so that brought me to the question of what's going on. How do you end up destroying such correlations between the particles in the pair created? At that time, that was sort of like an information paradox, and it reminds me of what goes on inside the horizon of the black hole and outside this question about, which has come up about the correlations between the members of the pair again. So it seems to be no problem in the expanding universe, I guess, you know, ultimately, but I had a solution. You can solve the problem in another way in the expanding universe, but I guess for the black hole it doesn't work because of the total evaporation that's supposed to take place. So anyway, it's interesting. I just mentioned it. Yeah.
I just want to make, since this diagram is on the board, I want to make a quick comment following up on Paul's comment in response to Laura's question. I put in a collapsing body. I just want to say I believe very strongly in this picture that I drew with the blue arrows, where there is something going into the black hole out here that is not originating in the body. And I believe that because in a two-dimensional model I can calculate it exactly. No approximations, no uncertainty in what the formulas are. It's a very, very simple formulas. And they describe this: positive flux going out here, negative flux going here. This positive flux does not originate down here. Let me remove that. And I understand, Laura, why you're concerned about the fact that the curvature that is acting as the source of this, okay, and that was another big contribution of Bill Unruh, to notice that in two dimensions, and specifically, The conservation law for the stress tensor is a set of first-order differential equations that tells you that the TVV and TUU, the independent components of the stress tensor that are not determined by the curvature, are determined by first-order equations that have the curvature scalar itself as the source. And now, your question, as I understand it from your question of Leonard several days ago, was how is it possible that this phenomenon is not invariant under time reversal? Why does the radiation go into the future and not into the past? And the point is that this is a very special situation which is similar to radiation from a classical radiation from an uniformly accelerated charge, and also analogous to the quantum field theory phenomena called Klein paradox or Schwinger effect, where there's a degeneracy of the vacuum state. For thermodynamic reasons, we usually assume that you start with nothing and the radiation comes out. But there are equally many, there are other solutions in which the radiation is coming in and disappearing, and other solutions in which you have as much coming out as you have coming in. And that's a very close analogy to the distinctions between Hartle-Hawking state and Unruh state. And I have a number of references I'd like to give you, but I don't want to carry on that dispute.
So are you saying that the collapse is not crucial to obtaining Hawking radiation?
The role of the body, the collapsing body, is to produce a Schwarzschild metric that extends all the way down to R equals 2m. Once you get that vacuum solution, or in 2 dimensions is not a vacuum solution, but something that is essentially the reduction of the 4-dimensional vacuum solution to the TR plane, then you can do quantum field theory in that background, and you find this kind of Hawking effect. But you don't need to produce the particles directly. It's a 2-step process.
So when we do that calculation for the quantum field, we define the state at past infinity. Suppose you choose the Unruh vacuum, right, and then you discover what happens near the surface of the collapsing star.
In the Unruh vacuum, and then you don't even need a collapsing star.
Yeah, well, that's my question. And then you see that future infinity with the detector and click when a Hawking radiation particle arrives there. Are you claiming that you can actually get the Hawking flux without the collapse phase? Is that what you're saying?
Yes, if you take the Unruh vacuum in the full space-time without any collapsing body there at all, then you get that result. You also get it if you start with a static star back here and then allow it to collapse. But the point of the Unruh vacuum was that it mocked up that result without actually having to consider the collapsing body explicitly.
So a static object, a nearly static object, such as a black hole, would give you the Hawking flux?
It's not really static.
Well, it evaporates in a solar mass black hole takes 10 to the power 75 years to evaporate. That's pretty static.
If you start with say a neutron star or something, and then it collapses.
No.
It's not static situation.
No, that's what we're going in circles now. I said forget about collapse because you claim the collapse is not important. So we start with a static star, and then we have this nearly stationary black hole.
I'm saying ignore the star entirely. Don't worry about it.
Yes. So you still get the Hawking flux.
The point is you have a horizon. You have something that looks like Schwarzschild metric with including the place where the coordinate system changes from static to mill or whatever.
Yeah, so that's exactly the situation I'm looking at. You have a static star and then bang, there is a black hole, no collapse. So, and the black hole takes such a long time to evaporate, you can think of it as nearly stationary. Are you claiming that you start with nothing and suddenly there is a Hawking flux for this nearly stationary black hole without collapse?
And I'll probably get the formulas wrong, but the basic formulas are the derivative with respect to v of t, v is equal to curvature scalar. Plus metric coefficients and so on that I don't remember. But any,
The equations are time reversal symmetric, but it's not the initial conditions that you're posing. And you have to argue that those are the right conditions to impose. We could argue about that, but the initial conditions that are being imposed are time asymmetric.
thank you. That's
Because
precisely my point. Thank you for making it more clearly.
Right, I mean, if you really have
Yes, please.
a static star, then there's no Hawking radiation. And there's also no horizon. But the existence of a future horizon means that the space-time is not static, because there's that region inside the future horizon which is definitely not static.
Yeah, I think there's really no plausible way to generate the Unruh vacuum without collapse.
Exactly.
I mean, formally, I agree with what Steve's saying, but I don't think in terms of physics, without collapse, you have any plausible way to get an Unruh vacuum state.
That was the question.
So I
Can you
think
get it
that's
without collapse?
In that sense, the collapse is absolutely crucial.
Yeah.
You need, yeah.
Yeah.
But I think.
I agree with Larry, but that doesn't mean that the outward radiation flux is originating inside the body.
Oh, I never made a statement about originating inside the body. I was just interested on the time when that is produced.
But I think there is one thing that, of course, the original Hawking derivation suffers from the problem of the transplanckian modes. That is, the modes that enter the body have to be extremely high and then be redshifted. And, of course, it's really, I don't think, as Jim pointed out in his talk, it's not very well defined where the particles are created. They're partly created somewhere in this region outside the collapsing body.
But no, that problem, it's easily addressed by speaking in terms of the stress energy tensor. The average wavelength of those particles is bigger than the size of the star. So, of course, it doesn't make sense to say they are produced inside or outside or somewhere 3m away.
Yeah, there is a difference between the stress energy and particles. That we have to be careful about that. But I think there is one thing that I don't think has been mentioned in this meeting and should be brought up, and that's the Corley-Jacobson idea. To get rid of the transplanckian modes by having a nonlinear dispersion relation. Of course, that has its price. It means you're giving up local Lorentz invariance. But if you do that, they've shown that you can, in fact, get Hawking radiation without transplanckian modes through a mode regeneration mechanism that creates the needed modes just when they're needed to be populated. Of course, they still need the collapse in order for their process to work, but it's happening outside the star and you don't need these modes of very high frequency skimming close to the horizon in their model.
I'll just say here, just one comment. I mean, there is still confusion about that, how important the collapse is to actually producing the flux, to the point that you'll hear people bring up the analogy with the Schwinger pair creation. And that argument goes, well, you can get a Schwinger pair created under a constant electric field. And again, the confusion there is the electric field might be a constant, but the potential associated with it is not. And that's exactly what's producing the Schwinger pair. So
No.
I just wanted to make the...
No, I disagree with that. The gauge invariant quantity is the electric field. It's once again the boundary conditions, the initial conditions that are asymmetric.
The electric potential is not, though.
Yeah, you can do it in a static gauge. That's a gauge-dependent statement. The electric field is time reversal invariant. A constant uniform electric field is a time reversal invariant state of the field, and there exist states in which particles are coming in from infinity and being destroyed. Mm-hmm. But you don't use those states because you think that's unphysical, and you put a different initial condition in which the particles are created. So I think the situation is analogous here. I think it's less clear to me. I mean, so I'll use this opportunity to say, I would like to add one more thing on that list, which I'm sure from your point of view is the most extreme, and that is that the Unruh state is not necessarily the unique initial condition, and there are nearby states in which there are large effects near the horizon, and this may happen something may happen at the horizon at formation. Now, the only reason that's considered extreme in this community is because physics is upside down. You're willing to accept singularities, you're willing to accept information loss, which, and usually in other areas of physics would be considered, a problem. But if you take that point of view, then, having something happen at the horizon looks extreme. On the other hand, trying to explain things by what I would call normal physics, namely counting states in ensembles, chemical, we have about 150 years of experience with. That is the way normal physics works, not information being lost in singularities. But that's my pitch, but I'll end.
Yeah, use the mic.
I have a question that maybe somebody here can answer. Before I get to my question, I want to say I agree with Larry about what he said a few minutes ago about burning the piece of paper. That's what the point I was trying to make with my example a couple of days ago about a anti-uranium nucleus producing a pion gas. It's very easy to start with a pure state and get something that looks thermal. And there's no big mystery about the whole thing. And I think that's what Larry was trying to say. Anyway, here is my question. In atomic or nuclear physics, when we emit a photon, we say the photon is emitted in the S wave or the P wave. It has angular momentum 0 or 1 or 2. Can somebody tell me what is the angular momentum of the photons from Hawking radiation?
Yeah.
If you naively multiply the temperature, the energy times the size of the black hole, you get a rather low angular momentum, which would mean that there are correlations in some sense in different directions.
No, it's emitted in all L modes, but the angular momentum barrier highly suppresses the very high modes.
So I made a mistake. The angular momentum is not low.
It's intermediate, but it's a range of angular momentum.
Okay, so then you've got correlations, some kind of quantum correlations in different directions. This question originated, I was asking Jim at breakfast to explain to me what Hawking said, and there was something about something happening on two spheres at infinity, which of course you would get if you have spherical harmonics with low angular momentum.
Well,
So where is the peak of the angular momentum distribution you're talking about?
I think it depends a little bit on the spin of the field you're dealing with, but it's
Well, let's
of
take
the
spin
order
zero field.
of a few. Jim, do you remember?
well, I'm not sure.
We can just Google it.
But in any case, the angular momentum.
I mean, remember, the angular momentum is a dimensionless number, so it must be some number you concoct out of the existing quantity.
If you're talking about electromagnetic radiation, there is no S wave, for instance, right?
Yeah,
yeah.
The angular momentum barrier is proportional to L squared, so it's going to grow very, very greatly as L gets large compared to 1. So if you want a number 2, 3, 4, something like that.
Okay, but that's what I sort of got. So does that mean then that if you have low angular momentum, of course there's some kind of correlations in different directions?
Well, I mean, in the case of Hawking radiation, it's very difficult for high angular momentum particles with the Hawking energy to get through the potential barrier, because it's a very large centrifugal barrier centered around R equal 3m, which prevents modes from going from inside to outside. So, so most of the Hawking radiation you expect to be in the lowest possible multipoles.
Yeah, so then you've got correlations in different directions. There's some kind of coherence, right? If you have low spherical harmonics.
Well, I mean, Hawking.
Usual angular momentum correlation, right? There's nothing unusual about that.
No, but I mean, it means that there's something coherent in the problem, right? with respect to different directions.
Yeah, I mean, sure. I mean, the Hawking radiation does not come out in one particular direction. It comes out, the quantum state, as it evolves, you have the Hawking radiation going out in all directions, and it's only correlations, there are correlations between different directions, but you can't say that the Hawking, a given Hawking quantum comes out in a particular direction. It comes out in all directions.
Yeah, but when you have an atom decaying in the S wave, of course it's equal in all directions, but there's a certain coherence which you don't have with totally random statistical emission.
Sure. So I just like, in connection with this, what Emil was talking about, the fact that you have the understate, which is well behaved in the horizon, and then neighboring states which aren't. There's an interesting paper by Lenny Susskind, which came out in July, called "The Typical State Paradox: Diagnosing Horizons with Complexity." And well, as a typical Lenny Susskind paper, I mean, there's a lot of conjecture, but I think it is an interesting paper and addresses this issue of how most quantum states in the vicinity of the horizon will involve things like firewalls and very messy physics, but that if you're talking about something evolving from nice initial conditions, as in the case of the Unruh vacuum, then while there may be some tendency to develop, into these much more complex states, the time scale for that, he argues, is much longer than the evaporation time of the black hole. So it's not really relevant to the evaporation problem. Anyway, if you're interested, read the paper.
We've got about 3-4 minutes left for this session, so I'm wondering if we could go quickly through points 3 and 4 in what Steve wrote. And I can say something about point 3, because we had 3 people talking on Monday about it, and I suppose the problem is very well defined. There is a collapsing star or a black hole, and there is a Hawking flux associated with it. And the question is, how does that flux modify the evolution of the star, of the collapsing star or the black hole? And in terms of procedure and formalism, all we have to do is solve a set of Einstein equations and the stress energy tensor conservation, and we're done. Whatever comes out of it, that is the answer. And we saw 3 different approaches to the problem of the back reaction by Gerard Toft, Jim Bardeen, and myself. They look different. I am curious. I think there is quite a bit of overlap between the 3 approaches. For example, Jim and I were both talking about negative energy fluxes going into the hole and doing something to the interior. So that will be an interesting problem to see how the 3 approaches overlap. When it comes to point 4, quantum gravity, I think if you may have noticed that word always comes up when we are stuck with the kind of problem that we either don't understand or where our theories break down, such as Einstein's theory of gravity and quantum field theory. So that's almost like a code word for saying we don't understand singularities and we don't understand what happens to these trans-Planckian modes being blue shifted to infinite energies near the horizon. So I suggest we take a vote on singularities. We all know that mathematically we do end up with singularities at the center of a black hole. That's been known since the 30s. But mathematically and physically are 2 different things, and we have learned that not all mathematical objects do necessarily exist. So I'd like to take a vote on how many people think there are really such physical objects in the universe, singularities.
Well, in terms of back reaction, I would just say that given, as I believe along with Steve Fulling, that Hawking radiation is not generated in the collapsing star, then and you can calculate the back reaction using the semi-classical energy momentum tensor. And it does not have any singularity near the horizon. It's perfectly, the effects are of order, fractional effects of order mp squared over m squared. And in a freely falling frame. And you can calculate the evolution, the evolution of this, assuming that since the semi-classical energy momentum tensor for a short-term black hole is spherically symmetric, you can still have a spherically symmetric space-time, the first order anyway, in the back reaction. You can calculate the change in the metric as a result of the back reaction using the Einstein equations, just the first order. That's all I claim the semi-classical approximation allows you to do. But it's a straightforward calculation, and you find that there's nothing strange happens. The geometry stays Schwarzschild and with small corrections.
If you're asking about mathematical singularities in classical relativity, I think like most people, I would say that quantum gravity probably has to do something to it, probably close to the Planck scale, but what, I have no idea. And whether that has any, whether that would solve an information problem is also a lot less clear. So I think I would say that singularities have to turn into something else, but what is not clear at all to me.
May I? Can you hear me? I don't know the answer to the information paradox any more than the rest of you. But one question I would ask is, in looking for a theory that might give us the right answer, would be, does it first give us the right answer for the microscopic Bekenstein-Hawking entropy? If it doesn't do that, its chances of answering this more difficult question are not very high. Now, string and M theory has an answer to the first question. Maybe there are other theories that do. But I'd like someone to address the question of how they think they're going to solve the information paradox without first solving the entropy problem.
And here comes the answer. Yes.
Let me just comment quickly on Mike's question. That is, certainly string and M theory have a calculation of entropy for extremal or near extremal black holes. So it's a partial answer. But it appears to me that it's a state counting argument. So it would not surprise me that to expect that there are a lot of theories that when they're worked out will be able to do a similar state counting arguments. So I agree that that's something that's a necessary requirement, but I think it's very far from sufficient. That you need a lot more than counting states to be able to say what's going to happen near a singularity.